you ever do this as a child? Maybe with one of your siblings. There's one piece of cake left or one cookie. You take half of it, then you take half of what's left, then half of that, and so on. Does the process ever end? At what point does the remaining piece become too small even to see? Let's say that after n bites, an is the fraction of cookie that has been consumed. That is, 1 minus an is the fraction of the cookie remaining. At the very start, n is 0, so the fraction of the cookie that has been consumed at that time is simply 0. After 1 bite, half of the cookie has been eaten. After 2 bites, 1/4 of the cookie remains, so 3/4 has been eaten. After 3 bites, 1/8 of the cookie remains, so 7/8 of the cookie has been eaten. After 4 bites, 1/16 of the cookie is left, so 15/16 of the cookie has been eaten, and so on. Now, at some point, the remaining portion of the cookie is just a crumb, and the fraction that has been eaten is almost exactly 1, but, okay, not exactly. In principle, you can imagine this process running forever, thereby generating an infinite sequence of fractions approaching 1 in the limit. None of the an's equals 1, but we say that the limit of the sequence is 1. The limit of an is 1, as the index n increases without bound, denoted here using the arrow. We say that the limit of an is 1, as n goes to infinity. Note that n is never equal to infinity. We're indicating that n is getting bigger and bigger without stopping. The limit can be expressed using an arrow to indicate that an approaches 1 as n approaches infinity. Here is another way we write the limit, and we read this as the limit of an as n goes to infinity is 1. To justify why the limit of an is 1, the easiest argument would be that the fraction of cookie remaining is 1 minus an, which is 1 over a power of 2. Now that fraction approaches 0 very quickly. The fraction of the cookie remaining is a fraction, like half, 1/4, 1/8, 1/16, etc. After each bite, only half as much remaining. And in principle, the fraction of the cookie remaining is never 0, but it approaches 0. It has a limit of 0. Here is a story that has been around for 2,500 years. This is one of Zeno's paradoxes, the story of Achilles and the tortoise. And I'm adapting it by adding a stopwatch and a few assumptions about the speed of Achilles and the tortoise. Also the initial distance separating them. Achilles is running a race against a tortoise. Achilles starts running from the starting line at time 0, but the tortoise has a head start. At some time t1, Achilles gets to the position where the tortoise started. I'll assume that time is 30 seconds into the race. But Achilles hasn't caught up yet because by that time, the tortoise has moved forward some distance. At some later time, t2, Achilles reaches the location where the tortoise was at time t1, but once again, the tortoise has moved on. At a slightly later time t3, Achilles reaches the point where the tortoise was at the previous time t2. Once again, the tortoise has moved ahead. And then at an even later time t4, Achilles reaches the point where the tortoise was at the previous time t3, but of course the tortoise has moved ahead again, and so on. Does Achilles ever catch up? And does he in fact pass the tortoise? Zeno wants to trick us into believing the answer is no. And of course, that's the deception. The way he tells the story, it takes several seconds for him to describe what happens for each integer n as time goes from tn to tn plus 1, as Achilles catches up to the previous position of the tortoise. At the rate of telling the story, it would take forever for Zeno to tell us how the race unfolds. But in real life, the time intervals from t0 to t1 to t2 to t3, etc., get shorter and shorter, and in much less than a minute, all the waypoints are behind the runners. all these infinitely many time frames have elapsed, and Achilles has passed the tortoise. In fact, the point in time at which Achilles is passing the tortoise is exactly the limit of the values Tn appearing in the story. I've used some simplifying assumptions here by supposing that both Achilles and the tortoise are running at constant speeds, and of course Achilles' speed is greater than the tortoise's speed. Also, an assumption about how much of a head start the tortoise has. These values will affect the actual numbers, but not the qualitative outcome. The gap between Tn and Tn plus 1 will necessarily decrease rapidly, so that Tn is approaching the limit, which will be the time at which Achilles overtakes the tortoise. It's usually said that calculus dates from the 17th century, being famously co-invented by Newton and Leibniz. But actually, the most basic concept of calculus, the limit, has been around much longer. The ancient Greeks came very close to inventing calculus, including Zeno, as we mentioned, but a couple of centuries after Zeno, Archimedes was able to calculate pi more accurately than anyone else until much, much later. Again, I'll oversimplify the historical details in order to simplify the mathematical explanation. Archimedes considered a circle of radius 1, which encloses an area of exactly pi. Right? That's pi times the radius squared, radius is 1. Archimedes considered an equilateral triangle inscribed in the circle. That's an equilateral triangle whose vertices all lie on the circle. Using some formulas for area known to the ancient Greeks, Archimedes knew that this triangular area was exactly 3 root 3 over 4. So pi must be larger than that. Next, a square inscribed in the circle has area exactly 2. So pi must be larger than that. An inscribed regular hexagon has area 3 root 3 over 2. So pi must be bigger than that. We don't really need to see the explicit value of an for every n, just enough values to see the overall trend. For a regular 16gon, for example, the area is given by this value, which you can see is starting to look something like pi. At least the first digit is correct. A regular polygon of 100 sides looks so much like a circle that you can't really see the difference at this pixel resolution. Its area agrees with pi to 2 decimal places if you round it up. If you take larger and larger values of n, the value an for the area is closer and closer to pi. In fact, the limit of an is pi. As n goes to infinity, the limit is pi. This observation underlies Archimedes' approximation of pi, which was accurate to about 3 or 4 significant digits. Here is another method for approximating pi, which came much later, in about the 17th century. We consider a sequence of approximations, starting with 1. The second term in our approximation is obtained by subtracting a third from the first term. Now we add 1/5 to that to get the third term. Then we subtract 1/7 to get the next term, and so on. You see the pattern? You'll notice that the terms in our sequence form a sequence of steps going up, down, up, down, up, down, and so on, alternating up and down forever, but with each step getting smaller and smaller. Here are the decimal approximations to the terms in our sequence. It's not hard to convince yourself that the sequence is going to converge to a limit somewhere between 0.7 and 0.8. Well, it turns out that the sequence actually converges to pi over 4. Here's the other way we like to write this limit. So you can cross multiply to solve for pi. So if you wanted, you could in principle use this as a way to approximate pi. Simply take a term far enough out in the sequence, something like the millionth term of the sequence, S1 million, and then multiply by 4, of course. Now, the number pi is not actually as special as most people think. Some people say pi is remarkable just because its digits go on forever. Big deal. Typically real numbers all have this property. Essentially all real numbers do. Every real number can be given by a decimal expansion. Consider this very unremarkable example, which I've called alpha, constructed by writing down digits randomly. What do we mean when we write a decimal expansion for this number alpha? Well, we get a sequence of approximations to alpha. Stopping at the nth decimal place gives us an approximation that I've called alpha n. By the way, you'll see that alpha 2 equals alpha 3, so there's really no requirement that any of the terms in the sequence are different from each other. The number alpha is approximately equal to alpha n, an approximation that is correct to n decimal places, meaning that the difference between alpha and the nth approximation is a very small number, at most 10 to the minus n in this case. Finally, let me say what is really meant by a limit. A sequence of numbers, A0, A1, A2, etc., is said to converge to a limiting number L, denoted with this arrow symbol, or with this alternative limit notation, if the following conditions hold. The terms of the sequence, the values an, approximate L to within any desired accuracy if you go far enough along in the sequence. For example, if we want an to agree with L to, let's say, 4 decimal places, then this will be the case beyond some point in the sequence. The first few terms in the sequence may or may not be such great approximations, but there must be some point beyond which all the remaining terms are within 4 decimal places of L. How far out in the sequence do you have to go? Okay, that's not really the relevant point. If you want the terms of the sequence to actually be much better approximations to L, let's say within 12 decimal places, then you have only to go even further out in the sequence, and this accuracy of the approximation will be achieved. And so on. In fact, for every specified accuracy, we require that the terms of the sequence will, beyond some point in the sequence, all be within such an accuracy of L. This is a strong requirement. Not every sequence of numbers will have such a requirement satisfied, and so not every sequence of numbers will converge to a limit. However, when a sequence has a limit, it can only have one limit, only one value for the limit. You should really take time to think about what we mean by a limit and how it applies in each of our 5 examples. The concept is both subtle and deep. We must agree that in order to understand how real numbers are represented by decimals, already presupposes at least a basic understanding of what a limit is. And herein lies one of the difficulties of learning calculus. You are expected to have a prior understanding of real numbers when you come into calculus. But the real number system is much deeper and more subtle than students generally realize. An understanding of limits goes hand in hand with a deeper understanding of the real number system. So be prepared to learn about both.